In this video, we'll continue our work with the Controller Area Network, or CAN. In Part 1, we configured the RA6M4 to transmit data over the CAN bus. Now in Part 2, we'll set up the RA6M5 to receive that data and echo it back to the transmitter. We saw that the RA6M4 requires an external transceiver to connect to the CAN bus. The same configuration applies to the RA6M5 as well. However, the EKRA6M5 includes an integrated CAN transceiver, allowing it to connect directly to the CAN bus via the CAN H and CAN L lines. The CTX and CRX lines are not connected to the transceiver by default. We need to short the solder bridges E34 and E35, located on the bottom of the board, to connect the MCU to the integrated transceiver. Once this is done, the CAN H and CAN L lines are available on the J33 header pins. Now that we got the hardware settled, let's open up E² Studio. We make a new RA project and choose the board EKRA6M5 for FSP preconfiguration. The first order of business is to add the CAN stack. Under the Connectivity tab, we can see the CAN FD stack. Let's add it. CAN FD, or CAN, Flexible Data Rate, is an enhanced version of the classical CAN protocol that supports higher data rates. However, for our application, we will use the classical CAN protocol. We also notice that the stack is highlighted in red. When we hover over the Info I button, we see that the clock associated with the CAN module needs to be enabled. First, we enable the CAN FD clock, sourced from PLL2. To do that, we also need to enable PLL2 and set its source to the external oscillator XTAL. Next, we configure the USB clock using the PLL and select the 24 times multiplier. Setting the division factor to 4 gives us a 48 MHz USB clock. Then we select channel 1 for the CAN FD stack. At this point, we can see there's another error to resolve. We now see an error stating that the configured channel has 0 acceptance filter rules. Since we're using channel 1, we need to assign the rules to that channel. To fix this, we set the channel 1 rule count to 32 and change the channel 0 rule count to 0. This clears the error. Since we're using channel 1, the acceptance filter list must match it. So we change the filter list array from AFL0 to AFL1, ensuring the filters are applied to the correct CAN channel. Next, we rename the callback function from CANFD0 to CANFD, simply removing the 0 to match our setup. We then assign the callback channel to channel 1, ensuring that interrupts and events are handled by the active CANFD channel. Next, there are a few additional settings we need to configure. First, under Flexible Data, we disable the protocol exception option since our protocol is classical CAN. For payload overflow, we select the reject option. Then, in the common FIFO settings, we enable FIFO3, set its mode to transmit, and enable the TX interrupt. In this example, transmission is performed using a common FIFO. As shown in the CANFD message buffer configuration, each channel has 3 common FIFOs. For channel 1, these correspond to common FIFO3, common FIFO4, and common FIFO5. Therefore, when writing to CAN FD-TX buffer, FIFO common 0, this refers to common FIFO3, which is the first common FIFO allocated to channel 1. We're going to check the reception FIFO 0 configuration and confirm that it is enabled. After that, we verify the CTX and CRX pin assignments for the CAN 1 channel. Once everything looks correct, we can proceed to generate the project contents. The CAN FD APIs look to be successfully generated. Now let's open the HAL entry file and move on to the coding part. First, we add the standard Boolean header file. We define 2 constants, one for the expected incoming CAN ID and one for the outgoing CAN ID we will transmit. This centralizes the IDs so they can be updated later without searching through the code. Next, we need a safe way to pass data from the CAN interrupt callback to the main loop. Since the callback should stay lightweight, we define frame variables for both received and transmitted CAN messages. We store the latest received frame in a global and flip a simple flag to let the main loop know new data showed up. We mark the flag as volatile because it's modified inside an interrupt. That way the compiler won't optimize out the checks we do in the main loop. Now we tell the CAN FD hardware which frames we want to accept, using the acceptance filter list, or AFL. We use developer assistance to generate the AFL structure and grab the filter entry we need. We configure it to accept only standard data frames with ID 0x004 and route them into RX540. No extended IDs, no ranges, nothing extra. The key line here is mask ID equals 0x7FF. That means all 11 bits of the standard ID must match exactly, so only ID 0x004 gets through. Everything else is filtered out directly in hardware. Next, we implement the callback function. The CAN driver calls this whenever something happens, like a receive completing, a transmit completing, or an error. For our use case, we only care about RX complete, so we read the frame from RX540, store it, and set the flag. We're doing the minimum work in interrupt context. Just read and flag. The main loop will do the transmit. Next, we move into the HAL entry function and start bringing up the CAN FD driver. The first thing we do is declare an FSP error variable so we can capture and check the return status from each API call. The API calls themselves come straight from developer assistance. We open the CAN peripheral to initialize the driver. Then we switch into reset mode so it's safe to change settings. While we're in reset, we configure it for classical CAN. Reset mode is required because some config registers can't be changed while the controller is active. This CFDC21 index must match your CAN FD channel. If your instance is channel 0, this should be CFDC20. Finally, we switch to normal mode so we can actually participate on the bus. Now we're in the main loop, and everything happens inside this infinite while loop. On this line, we check the gCAN RX pending flag. This flag is set by the CAN interrupt callback when a new frame has been received. When the flag is true, the first thing we do is clear it. That prevents us from processing the same frame again. Next, we copy the received CAN frame into our transmit frame structure. This preserves the DLC and all the data bytes exactly as they came in. On the next line, we override the CAN ID and set it to our transmit ID. Here, we explicitly set the ID mode to standard, make sure the frame type is a data frame, and clear any optional flags. Finally, we write the frame into the transmit FIFO using the CAN FD driver. On this last line, we assert that the write succeeded, so we'll catch any errors during development. Here are the hardware connections. As shown, the RA6M4 requires an external transceiver, while the RA6M5 can use the onboard transceiver. Both devices are connected to the common CAN-H and CAN-L lines on a small breadboard, with termination resistors in place. The end result is simple forwarding. Frames received on ID 004 are retransmitted on ID 0020 with the payload unchanged. And that brings us to the end of our two-part tutorial on exchanging data between RA devices over the CAN bus. See you in the next video.